All right, welcome everyone. So today we're going to finish off talking about logarithmic differentiation. So finished looking at our differentiation techniques. And then we're going to start talking about applications of derivatives, which is really going to be the focus of the course for the next few weeks. We're going to be talking a lot about applications. And so the first one we're going to look at is exponential growth and decay. All right, so that's what we're going to cover in lecture today. Just a reminder that for this week, we have our third recitation exam during your scheduled recitation time. So, have a look at our assessments page on UB Learns to see, to have an idea of how the exam will look. I posted a sample exam there so you can kind of read through the directions and, know what to expect ahead of time. All right, so let's get into it. And today, like I said, we're going to finish off talking about logarithmic differentiation. And so we calculated the derivative of this function last time. It was y equals t minus 2 divided by 2t plus 1, all raised to the power 9. And last time we did it, we used the general power rule, and then we used quotient rule. This time, we're actually going to use the technique of logarithmic differentiation so that we don't necessarily have to use all of those rules to calculate the derivative. All right, so let's try it out. And we have a description of how this process works. So the very first step is to apply the natural log function to both sides. So let's do that. So we're going to do the natural log of y on the left. And this is the first step. And then this will be equal to the natural log. And one thing I'm going to rewrite right away is that exponent raised to the power 9. When we have a fraction all inside a power like that, we can think of it as distributing that exponent to the numerator of the fraction and to the denominator. So we could think of this 9 as going on to the t minus 2 part, and then we could think of it like distributing onto the denominator. So we can only distribute exponents like that for multiplication and division. So we have division here, we can distribute that exponent. So I'm going to think of this as t minus 2 raised to the power 9, and then in the denominator 2t plus 1 raised to the power 9, and all of that is inside the natural log function. All right, so that's our first step. Just apply ln to both sides. Now in step 2, we're going to simplify, and there's nothing really to simplify on the left there. All of the action is going to happen on the right. So let's use our log rules. So we saw those last time, and when we have a fraction, that becomes the natural log of the numerator minus the natural log of the denominator. So log has these nice properties that simplify a lot of the arithmetic down. So it converts this division essentially into subtraction in some way. Now there's also a property that lets us take those exponents, move them outside of the natural log and put them in front. So instead of having the 9 here and the 9 here, I'm just going to move those out and put them in front of the natural log. So I'll put the first 9 in front of that first natural log, and then I'll put the other 9 in front of the other natural log. So we have this simplified expression now of natural log of y equal to 9 times the natural log of t minus 2 minus 9 times the natural log of 2t plus 1. So that's about as far as we can go. When we have addition or subtraction inside the log function, we can't simplify that any further. So that's about as far as we can go. And now in step 3, this is where we do implicit differentiation. And most of that is on the left-hand side. So on the left-hand side, we have natural log of y. So there we see a y term. So we're going to differentiate it like usual. So 1 over y. And then we'll multiply that result because we're differentiating a y term. We differentiate like usual. So derivative natural log of y is 1 over y. And then we multiply that result by y prime. And then on the right-hand side, these are all just regular variable functions. So we can just differentiate all of these like usual. So that first natural log term, the 9 is a constant multiple, so it just stays in front. Then when we differentiate that first natural log function, we get 1 over t minus 2 times the derivative of t minus 2. So we're using the general chain rule there. So it's 1 over the inner function times the derivative of the inner function. That's the general log rule. Then we go on. We have the minus 9. So that 9 is a constant multiple. It just stays in front. And then we differentiate that second log function. So derivative of ln 2t plus 1 is 1 over 2t plus 1. And then we take that inner function and multiply by its derivative. So we need to differentiate that inner function 2t plus 1. All right, so that's the differentiation. And then we just keep going. So we just finish off the differentiation. So anything that we have left to do, let's do it. So I'll put the 9 on top of that fraction. So we get 9 over t minus 2. And then the derivative of t minus 2 is just 1. So I'm not going to write the 1. And then I'll move that 9 on top of the other fraction. So we get minus 9 over 2t plus 1. And then the derivative of 2t plus 1 is 2. So we'll have that multiplied by 2. And the very last step then is to solve for y prime. And so what we're going to do is we're going to multiply both sides of this equation by y. And why do we do that? Well, on the left there, the y and the 1 over y would cancel, leaving us with just y prime. And then the very last thing we need to do is just to fill in what we know y is. So ultimately then we get y prime is equal to, and we'll put the y term first. Doesn't really matter, but we'll put it first. So let's fill in what we know y is. It was that original fraction all raised to the power 9. And then we have it multiplying, and then we could just fill in what we found from before. So 9 over t minus 2 minus, and I'll simplify the arithmetic there. I'll do the 9 times 2 to get 18. So we have 18 over 2t plus 1. And there's our derivative. So we didn't have to use quotient rule in there, and we didn't have to use general power rule. Now, we did have to use the general log rule, but, you know, might not be as bad. Usually this one I would probably, if I were to do this one, I would probably just do the general power rule and then do the quotient rule. Use that approach, but logarithmic differentiation works perfectly well here. So really log differentiation is a technique when you have, you know, maybe if you had like 3 rules that you would have to use. So maybe if you had like a general power rule and a power rule and a quotient rule, then you might start thinking about log differentiation. This one, either approach would work about the same amount of work. Either approach works just as fine. All right. One more example, and this one we really have to use logarithmic differentiation for. So the function here is y equal to x raised to the power square root x. And this is a pretty unusual function. Normally, you know, we don't see these types of functions. I don't think we've seen them too much, at least in the course so far, where we have a variable base term and we have a variable exponent. So we don't see this type of thing too much. So we have a variable base and we have a variable exponent. Normally it's one or the other. Normally it's like e to the x, where the variable is in the exponent. Or it's like x squared, where the variable is the base term. We don't see too many of these where both the base and the exponent are variables. But if we do see one like that, logarithmic differentiation is the technique to use. So let's go through it again. Step 1, we're going to apply the natural log to both sides of our function here, of our equation. So we get natural log y is equal to the natural log of x raised to the square root x. In step 2, we simplify using our log rules. So natural log y, nothing really to simplify there. But on the right side, that exponent can come in front of the natural log term. So we could write that as square root x times the natural log of x. Once we do that, then we go through our implicit differentiation. And really the only implicit differentiation is happening on the left when we differentiate that natural log y term. So it's a term with y, and we're treating y as both a function and a variable. So we differentiate it like usual. We get 1 over y. And then we multiply the result by y prime. So that's on the left. And then on the right-hand side, we want to differentiate square root x times natural log x. Now it's just functions of x, so this is just regular differentiation over here. But when we look at this, we have a product. So this is multiplication. And there's variables on either side of that multiplication. So there's a variable term on the left, square root x, and then there's a variable term on the other side, the natural log x. So when we have two variable terms being multiplied together, we have to use the product rule. So we want to apply the product rule. So we write down 2 copies of our function. Put a plus sign in the middle. And then in the first copy, we apply the derivative to the first function. And then in the second copy, we apply the derivative to the second function. So derivative of natural log x. All right, so there is our work for the differentiation. We still have a few more to do there, but those are just basic derivatives now. So we just keep going. So we'll leave our left-hand side. Won't do anything over there. Let's differentiate that square root x. And to do that, let's just remember that we could rewrite square root x as x to the 1/2. So when we do that derivative, it's just the power rule. So we bring down the 1/2, keep x the same, and then we subtract 1 from the exponent. So we get 1/2 x to the negative 1/2 power. The natural log is outside the brackets, so we're done with that. It just stays the same. Then we go on, and while we're at it, let's write that other square root x as x to the 1/2. It's not changing it in any way. It's just rewriting it. And then finally, we need to differentiate that natural log x, and that's just 1 over x. So just one of our basic derivatives. And there we go. We're done differentiating. And now all that's left to do is in step 4, we want to solve for y prime. So we're going to multiply both sides of our equation here by y. And why do we do that? Well, on the left, the y and the 1 over y just cancel. And so what do we end up with? We get y prime, and then we just want to fill in what we know y is. So we know y is equal to x square root x, so we're going to fill that in for this y term on the left. And I'll just write it first, but it doesn't really matter where you write it. But I'll put it first here. So x square root x. And then we can do a little bit of simplifying on the terms inside the big set of parentheses here. So both of these terms end up having a 1 over x to the 1/2 power. So we can actually factor out a 1 over square root x. And then we have a 1/2 natural log x minus 1 term left over. So where you can see this is this x to the 1/2, this x to the negative 1/2 is really 1 over square root x. And then the x to the 1/2 times 1 over x, if you do that multiplication, you also get 1 over square root x. So both terms inside that big set of parentheses there has a 1 over square root x, so we can factor that out. Again, not really necessary to simplify like that, but it could be helpful. And that's it. We differentiated, we have y prime, everything's in terms of x on the right-hand side, so we're done. So let's just kind of review what happens when we have, so we were looking in that last example, how to differentiate when the exponent and the base terms were both variables. So that really kind of completes all of the different techniques that we would need in order to differentiate a term that has an exponent. So let's look at all four cases here. So in the first case, let's let b and n, these are just constants for the purposes of this chart. So let's say that we saw in our function b raised to the power n, where both b and n are constant terms. So when everything's a constant, when both the base and the exponent are constants, well, that function is just a constant term, so that we know the derivative of a constant is 0. So the derivative of b raised to the power n would just be 0. Now what happens if we see x terms in the base? So it's some x terms all raised to a constant power. So something like x squared or x squared minus 1 all cubed. Well, in that case, we would use the general power rule. So we differentiate the outer power function just like usual, and then multiply by the derivative of the inside. If we were to see x terms in the exponent, so these are things like e to the x or e to the x squared plus 1. When we see the exponent is where the variable terms are, then we have to use our general exponential rule. So derivative of b raised to the power ux, very generally, is b raised to the power ux times natural log b, and then we multiply by the derivative of those terms in the exponent. So both of these are really just examples of the chain rule. And then finally, we talked about it in that last example. If we have a term where there's both variables in the base and the exponent, that's this last case here, and really there's no nice little formula for this one. It's just you have to go through the process of log differentiation. So this last case here is where there's x terms in both the base and the exponent, and that's where logarithmic differentiation comes in. All right. So that'll do it for just our techniques of differentiation. So that's really what that section, we called it Learning Outcome D, just all of our standard differentiation techniques. So what we're going to start next is we're going to start looking at applications of derivatives. And the first one we're going to consider is how to solve problems involving exponential growth and decay. All right, so let's look at our first motivating example here. Let's suppose that we have a population of a bacteria culture that doubles in size each day. And let's suppose that initially there's one bacterium that's present. What we're going to do in this little example is we're going to determine the size of the population after 3 days. All right, so let's consider day 0. Time 0. What do we start with? Well, we start with one bacterium. So there's our little bacterium in our culture. And so we initially start with, at T0, we start with one bacterium. So let's plot that on our little exponential on our graph here. So at time 0, we have one bacteria. Now let's suppose that we let 1 day go by. And what happens over the course of that day is that bacteria splits and it forms 2 new bacteria. So the population doubles in size over the course of that 1 day. So this one bacteria splits, and now we have 2 daughter bacteria cells. All right, so that's after day 1, and now there's 2 bacteria here. So let's plot that after day 1. The size of our population is 2. Then let's look at t equals 2. What happens if another day goes by? Well, that first, each bacteria then is going to split again. So this bacteria is going to split. So we get 2 new daughter bacteria. And then this bacteria is going to split. So we're going to get 2 daughter bacteria from that one. And so if we look at this, we're going to have 4 bacteria present in our culture after day 2. So let's plot that on our graph as well. So on day 2, we're going to have 4 bacteria in our culture. And let's see what happens after day 3. So we let 1 more day go by, and then each of those bacteria that we have that are present on day 2, each of those is going to split. So that first one is going to split. That second one is going to split, and each of them splits into 2. And then finally that last one splits. So if we count them up, how many bacteria are present there on day 3? Well, there's 8 of them. And so let's plot that on our graph. So after day 3, there's 8 bacteria present. And what we see is that these data points fit an exponential curve. So what we're going to see in a few seconds is that this population is experiencing what we call exponential growth. So its data points fit along an exponential curve. All right, let's just look a little bit more at what's actually happening with the population going from each day, progressing along each day there. So we call the initial population, we usually call this P0. And then so what happens going from day 0 to day 1 is that initial population gets multiplied by 2. Then going from day 1 to day 2, we take the previous population and we double that. So we multiply that by 2. And then finally, to go from day 2 to day 3, we take our previous population and we double it. So we multiply that by 2. So after each day here, our population is doubling. And really, if we think of that in terms of powers of 2, we could rewrite this first one as P0 times 2 to the power 0. We could rewrite the second population as P0 times 2 to the power 1. P0 times 2 squared, and then P0 times 2 raised to the power 3. And so what we're doing here is we're really multiplying by powers of 2. And it's the variable term that's changing, or it's the exponent term that's changing. So that's where our variable is. So that's why these data points are fitting along an exponential curve. It's because the exponents it's the thing that's changing. All right, let's look at this a little bit more closely now and in the context of derivatives. So we say a population or a quantity is said to be growing exponentially if at every time t, the rate of increase of the population is proportional to the size of the population. And let's look at what this says in terms of a differential equation. So this is the first differential equation we're going to be looking at. Actually, it's the only one. Yeah, I don't think we're going to look at any more differential equations. But you know, if you keep going on with the math courses, there's a nice whole course devoted for a whole bunch of courses devoted to differential equations. So this is the very first one that we're going to look at. And what does it say? So it says the rate of increase of the population. So as soon as we see that word rate of change, rate of increase, rate of decrease, anything that's changing, that is a derivative. So the rate of increase of our population, that's just another way of saying the derivative of p. So that's what we see here in these equations. This is our rate of increase. And then in the denominator, we see p of t, and that's just the size of our population. So what it means to be exponentially growing is that at every time t, the derivative is proportional to the function. So what it means to be proportional is that their quotient is equal to a constant. So when you take the one quantity and divide it by the other quantity, you get a constant term. In this case, we call it k. So the derivative p prime divided by the function p should equal a constant for each time t. Now, we could rewrite that not as a fraction. So if we multiply p of t to both sides, we get p prime of t is equal to k times p of t. And so this is a differential equation because it involves a derivative and a function. The derivative of an unknown function and the unknown function itself. So p prime is equal to k times p. Now it turns out this one is not too difficult to solve, and so the solution for that differential equation is our exponential growth function. So p of t is equal to p0 times e raised to the power k times t. And so p of t, like we said, is the population, it's the size of our population at time t. P0 or P naught is our initial, it's our starting population. So it's the initial population and that really happens at time t equals 0. So it's the population we start with at time t equals 0. And then we call k, that constant of proportionality, because we're talking about it in the context of some population or quantity that's growing, we call this our growth constant. All right, so this is our exponential growth equation. And let's just actually check that it's a solution for that differential equation. So let's calculate the derivative of our function here. Let's calculate the derivative of that. So p prime is equal to, now it's an exponential function, so we have to use our general exponential rule. P0 is just a constant, so it stays in front. Derivative of the exponential part stays the exponential part, so e to the kt. And then we take the term that's in the exponent there, and we multiply by its derivative. So derivative of k times t. And the derivative of that is just k. And so if we notice, this whole term right here, this is our function p of t. So if we simplify this, we get k times p of t. And so what this shows is that p prime of t is equal to constant k times p of t. And so this shows that it's a solution. For this differential equation. So that's all we're doing there. By just calculating the derivative and showing that we end up with that differential equation, this is just showing that it's a solution for this differential equation right here. Now, just a few other comments about this exponential growth function. Because we're talking about exponential growth, k here is positive. So it's growing, so the growth constant would be positive. And then there is an alternative format that we could think of as well. So there is an alternative form for this growth equation, and it's to write it in terms of the exponential function with base 2. So we could think of this as the population is equal to the initial population times 2 raised to the power little t over capital T. And in this alternative form, capital T is the time it takes for the population to double. And that alternative form, that's more in line with what we were seeing in our kind of motivating example, where we were just multiplying consecutively by larger and larger powers of 2. So this is just another way to think of our exponential growth function in terms of base 2. And if we recall, why does that work out? Well, there is a change of base formula. So we saw this last time where we had b raised to the power x, and we could rewrite that as e raised to the natural log b times x. So that's just a change of base formula for exponential functions. So if we look at this 2 raised to the power 1 over t, or 1 over capital T times lowercase t. So lowercase t is our variable, it's our time variable. Capital T is going to be a number, it's the time it takes for the population to double. So if we rewrite that exponential as 2 raised to the power 1 over capital T times lowercase t, and then apply the change of base formula there, we get e is equal to the natural log of 2 times 1 over capital T times lowercase t. And then we see what k here actually is. So we can think of k, the growth constant, as the natural log of 2 divided by the time it takes for the population to double. So, you know, either approach is fine. You could use the standard exponential growth formula with e, or you could use that alternative form with base 2. So either one's perfectly fine. Most of the time we're going to be using the e because, you know, it's calculus and the natural exponential function is a little bit easier to differentiate. So let's look at an example. Let's say that we have a colony of fruit flies that grows at a rate proportional to its size. And initially there's 20 fruit flies that are present, and then after 5 days there are 400. We want to determine a function that expresses the size of this colony as a function of time, where time is measured in days. So we're going to be paying attention to units here. But let's first see what we have to work with. And the first thing we notice is that the flies are growing at a rate proportional to its size. So that means we're talking about exponential growth. So that means that gives us a starting point. That gives us our exponential growth equation. So the population at time t is equal to the starting population times e raised to the power kt. And so when we write that, we want to determine that function p of t exactly. So we need to do two things. We need to first, well, we don't necessarily have to do this first, but we want to determine the starting population, p naught, p0 there. And then we also need to determine what that growth constant is. We want to determine what k is. So that's where we're going to use the other information that's given to us in order to figure out those two values. So if we look, we're actually told that initially there's 20 fruit flies. So we're actually given p0. It's equal to 20. So let's update our growth equation there. Let's fill that in. So the population at time t is equal to 20. We're just filling that in now. Times e raised to the kt. We don't know what k is, so we still have to find that. And then let's see what other information we're given. So we're told that after 5 days there are 400 fruit flies. So that's sort of our second piece of information that we're going to use. So let's write that down. So really what that's saying in terms of, let's write it down using function notation here. It says that if we were to evaluate our population function at t equals 5, we would get 400. So really that's telling us that p of 5 is equal to 400. So let's fill that into our function. So we know our function is 20 times e to the k times t. So let's fill 5 in for t. And we know that this population, when t is equal to 5, it should be equal to 400. And so what this does is it gives us an equation that we can use to solve for k. So we're going to use that equation there to solve for k. And this is going to take a little bit of work. So let's start with that equation. 20 e to the 5k is equal to 400. And we want to solve for k. So we have to first get the exponential term all by itself. So we're going to divide both sides by 20. So when we do that, we get e to the 5k is equal to 20. Now we want to cancel off that e. And so the way that we get rid of an exponential function is with its inverse function, and that's the natural log. So we're going to apply the natural log to both sides. So when we apply the natural log and the e there cancel out, and we're left with just 5 times k on the left. So we get 5 times k is equal to the natural log of 20. And then we want to solve for k. So we keep solving for k. So we're going to divide both sides by 5. And that gives us k is equal to the natural log. K is equal to the natural log of 20 divided by 5. So that's not the answer. We wanted to find a function that expresses the size of the colony as a function of time. So we just need to take that k value and plug it into our function p of t. So p of t then is ultimately 20 times e. And then instead of k, it's natural log 20 over 5 times variable t. And that's our population function. That's the population at time t. All right, let's try another example like that. We're just going to be given a little bit different information here. So let's say we're looking at a colony of fruit flies here, and it's exhibiting exponential growth. So the fact that we see that word that phrase exponential growth, another way of saying that the rate of the population change is proportional to the population size, along the same lines there. That does give us some information. It tells us that the population function p of t is equal to p0 times e to the kt. So we know we need to determine what p0 is, what the initial population is, and then we need to figure out what k is. So if we look at this, we're actually told what the initial size is. It's 100. So let's just write that down. P of 0 is equal to 100. And then we're also told that the population doubles in 9 days. So if we were to write that in function notation, what that's telling us is that the population at time t equals 9, p of 9, is equal to 2 times our starting population, so it's doubled. And so if we plug in what we know our starting population is, we would get 2 times 100, or 200. All right. So the first part here, we want to determine our growth constant k. And so we have our function. We have an idea of what our function is going to look like. We know our starting population. And then we also know that the population after 9 days has doubled. So let's take this equation here and let's evaluate it at time t equals 9. Let's see what we get. So we get p of 9. So wherever we see a t, just change it to a 9. So we get p of 9 is equal to p0 e to the k times 9. So wherever I saw a t, I just changed it to a 9. And what do we know about the population after 9 days? Well, this should be double the initial population, so 2 times p0. And if we look at this, this gives us an equation then that we can use to solve for k. And right away, doesn't matter what the initial size is because we see that p0 on both sides. So that actually we could divide both sides by p0 and cancel that off. So when we look at this, we get the equation e raised to the power 9k is equal to 2. And we want to keep solving for k there. So the way to cancel off an exponential function is to apply the natural log function to both sides. So we apply the natural log. To both sides. And on the left, the natural log and the e cancel and leave us with just that 9 times k. So we get 9 times k is equal to natural log 2, and then divide both sides by 9 to get k. And so there's our growth constant k. It's natural log 2 over 9. All right. So now this gives us a now we have all the information we need to find our function p of t, have a nice formula for our function p of t. So let's write that down. Our initial population was 100, and then our k value was natural log 2 over 9. So our population function, p of t, is 100 times e raised to the natural log 2 over 9 times t. And so we can use this then to answer questions like, how large will the colony be after 41 days? So all that's really asking is, it's saying, let's evaluate this population function when t is equal to 41. So wherever I see a t, I'm going to plug in 41. So that gives me p of 41 on the left. And then I have 100 e raised to the natural log 2 over 9 times 41 on the right. Now you could just leave your answer like that. But just to give a little bit of context, we could plug that into a calculator, and that's approximately 2,350. And the units here are fruit flies. So after 41 days, there's approximately 2,350 fruit flies. All right, what other kinds of things could we answer? Well, we could look at how fast our colony is growing after 41 days. So this is when we see how fast is our population growing, when we talk about a fast or increasing or decreasing or rate of change, we're really talking about there is the derivative. So this is asking us, really it's saying, let's determine the derivative evaluated at t equals 41. So what is our differential equation? Any quantity that's experiencing exponential growth satisfies this differential equation. P prime of t is equal to k times p of t. And so we can use this differential equation then to figure out what the derivative value is. So if we were to evaluate, well, let's actually just fill in what k is for this particular example here. So we get p prime of t is equal to, our growth constant k was natural log 2 over 9. And then let's fill in what actually our population is. It's 100 e raised to the natural log 2 over 9 times t. And to find our derivative value, we can just plug in 41 wherever we see a t value, a t variable. So we get natural log 2 divided by 9 times 100 times e to the natural log 2 over 9 times 41. And this whole quantity here, we just calculated that in part 2. That's just our population at time 41. So basically what we're doing here is we're taking our previous result, the population at t equals 41, and just multiplying it by k, and that gives us our derivative. So if we were to that's perfectly fine. We could leave our answer like that. But if we wanted to provide just a little bit of context, we could, plug it into a calculator and get a decimal out. So again, we're just taking our k value, which in this case is approximately 0.077, and we're just multiplying it by the population that we found from before at t equals 41. We found that was 2,350. And then if we do the arithmetic there, we end up with 181. And this is just an approximation because we're, it would be a decimal. But this is just to provide a little bit of context here for, what this derivative value looks like. And what are the units? Well, we're talking about the derivative, so it's a rate of change. So it's the population change. So it's the amount of fruit flies, but it's a derivative, so it's the rate of change with respect to, in this case, time. And time is measured in days. So it's, in this case, fruit flies per day. So after 41 days, the population is increasing at an approximate rate of 181 fruit flies per day. So this approach was just using the differential equation to calculate p prime. Another way, you could just calculate it directly. So you don't have to go back necessarily to the differential equation. We know what function p is, so you could just differentiate it directly. That's fine as well. All right, one more part here. At what time will the colony contain 800 fruit flies? So we can use that function we found, the function p of t, to kind of make estimates or kind of anticipate what happens at a future date. And that's really what we're going to see here is we want to figure out when is our population going to reach 800 fruit flies. And so to do this, we're going to set our function p of t equal to 800, and then we're going to solve for t. So let's start by writing down our function p of t. It was 100e raised to the natural log 2 over 9 times lowercase t, our variable t. And we're going to set this equal to 800. Now this gives us an equation that we can solve for t. So this is the equation we're going to solve for t. And the first thing we could do is divide both sides by 100. So the variable part is, the variable is up in the exponent. So we want to get, first of all, we want to get e by itself. So we're going to take that number in front and divide both sides by it. So we're dividing both sides by 100. This gives us e raised to the natural log 2 over 9 times t is equal to 8. We want to cancel off the exponential function, so the way we cancel e is with its inverse function, natural log. So we're going to apply natural log to both sides. That gets us the cancellation there on the left. So the left-hand side then becomes natural log 2 over 9 times t, and this is equal to the right-hand side, which is natural log 8. And then finally, we want to solve for t, so we want to multiply both sides by 9 and then divide both sides by natural log 2. So basically just multiply both sides by that fraction that's in front of the t term there. And if we do that, we get t is equal to 9 times natural log 8 over natural log 2. And if we do the arithmetic, that ends up being 27. And what are the units? Well, for this problem, lowercase t was measured in days. So what this tells us is that after 27 days, if our fruit fly colony kept experiencing exponential growth, after 27 days, its population would reach 800. All right. So that's exponential growth. Now, and that's where our constant is, the constant k is positive. We're also going to talk about exponential decay. And the example we're going to consider the most for this is radioactive decay. So first, just a really brief description of what radioactive decay is. It's the process in which the unstable nucleus of a radioactive element decomposes by emitting particles. So let's just consider a little kind of graph or a picture of what's happening here. So let's say we have our unstable nucleus. So we have some element here, and it's a radioactive element, and this is our unstable nucleus. What happens, we're not going to get into too much of the details, is it breaks apart and it forms a changed nucleus. So the nucleus is changed in some way, and it changes by emitting some particles. So we have some particles that it emits. And like I said, we're not going to go too much into the actual, what's really happening here. We're going to look at more of the quantitative side of what's happening. And so this is our changed nucleus. So an element that undergoes radioactive decay, there's an unstable nucleus, and then it changes in some way into a changed nucleus along with some particles that it emits. And so what we're looking at here is we have some original material, and then once it goes through that process of radioactive decay, it produces some new material. And what we're going to be considering is the question of how much of that original material is left as it undergoes this process. So the new material might be also radioactive, it might not be, but we're looking at that original material. How much of that original radioactive material is left? And so another bit of terminology here is we often talk about the half-life of the radioactive material, and it's the length of time that's required for a given quantity to decay to 1/2 of its original mass. So let's look at this with a little motivating example here. So let's suppose that we have a radioactive element and it has a half-life of 1 day, and we start with an initial mass of 1,000 milligrams. And we're going to see what happens to the mass of that original radioactive material after 3 days goes by. So let's look day 0. What do we have? So we have our sample, and I'm going to make that a little bit bigger. We have our sample, and it's all radioactive. So there's 1,000 milligrams here. So let's plot that on our graph. At time t equals 0, we have 1,000 milligrams. It's the size of our population. In this case, the population, how much mass, how many what measure of radioactive elements do we have? We have 1,000 milligrams there at T0. Now, let's let 1 day go by. So we still have our sample. But now the half-life of that radioactive element is 1 day. So after 1 day, the amount of our radioactive element is cut in half. So we take half of it, and that's what's radioactive. The other part is just some new material. Maybe it is radioactive, but that's not what we're interested in. We're interested in how much of our original element is still present. So going from t equals 0 to t equals 1, the size is cut in half. So we're down to 500 milligrams of our original radioactive element after 1 day. So let's plot that on our graph here. So after 1 day, we're down to 500. Then let's let another day go by. So now we're on to day 2. We still have our sample here. But now that original radioactive material that we have on day 1, that gets cut in half. So now we're down to here. So this is the amount of radioactive material that's left on our second day, and the rest is whatever new particles and new elements we get there from the decay process. So we have a portion of our sample is the original radioactive element, and then the rest of it is the new stuff that we get. And so this was cut in half. So we had 500 on day 1. Now we're down to 250 on day 2. It's cut in half. So let's plot 250 on our graph. So on day 2, we're down to 250. And let's look at one more day. So we're going to look at the third day. So we still have our sample here sitting around. But now the radioactive element has decayed even further. And so the amount that we had from before is cut into half. So now we're down here. This is all the radioactive element that we have. And then the rest is whatever the new substance is. So it's all of this. This is all of our new stuff. So how much of our original radioactive element is still there on day 3? 125 milligrams. It's cut in half yet again. So we go from 250 down to 125. And let's plot that on our graph here. And so when we look at this process, what's happening is our data points fit an exponential curve. This time it's of the form e raised to the power kt, where k is negative. So that's when we have an exponential function that's decaying like that, the exponent is negative. So k is negative. Let's think of it, though, in terms of kind of like what we did for population growth, where the population was doubling. Here the population is getting cut into half each day. So let's think about it in terms of powers of 1/2. So on day 0, we start with our initial population, the additional mass, the initial mass. Then after 1 half-life goes by, we multiply our starting mass by 1/2. Then another half goes by, half-life goes by, so we multiply our previous mass by 1/2. And then on day 3, another half-life has gone by, so we take our previous mass, which was p0 times 1/2 times 1/2, and then we multiply that by 1/2. And so what's happening each time a half-life goes by, essentially what we're doing is we're taking our starting mass and we're multiplying it by a power of 1/2. So in the first case there for t0, it's p0 times 1/2 raised to the 0 power. On day 1, it would be p0 times 1/2 raised to the power 1. And then on day 2, it would be p0 times 1/2 raised to the power 2. And then on day 3, it would be p0 times 1/2 raised to the power 3. So each time a half-life goes by, essentially, we've multiplied the previous quantity by 1/2. And so we see that the base term there is 1/2, and the exponent is what's changing. And so that's why our data points are fitting along this exponential curve, is because we really have an exponential function that we're talking about. So let's see the formula exactly. And it looks very similar to our exponential growth. So we say that a quantity is decaying exponentially if at every time t the rate of decrease is proportional to the quantity itself. So again, the rate of change is just the derivative, and then it's proportional to the quantity. So we get this differential equation, p prime is equal to k times p. Very similar to, so really not too much different here mathematically in terms of comparing this to exponential growth. So this is very similar to our exponential growth definition, except the only difference here is that that constant k is going to be negative, and that's because the quantity is decreasing. So if our quantity is increasing, k is going to be positive. If it's decreasing, k is going to be negative. So let's look at our exponential decay function. It says p of t is equal to p0 times e to the kt. Exact same function. But a lot of times, to really stress that the exponent is negative, we rewrite that as negative lambda times t, where lambda is positive. So that's just really to stress that our exponent is negative. Negative lambda times t. All right, so what do the quantities here represent? Well, p of t represents the mass of the radioactive element. At time t. So it's how the quantity after time t. P0 is our starting mass. So it's how much radioactive element we start with at time t equals 0. And then we call lambda the decay constant. And so there is an alternative format for this exponential decay formula if we were to think of it in terms of powers of 1/2. And we could write this instead as P of t is equal to P0 times 1/2 raised to the power t over capital T, where lowercase t is our variable and uppercase T there is the half-life. So it's the half-life of our quantity, of our material that's decaying. So that's just another way to think of it. And that agrees more with what we just saw in our little discussion there on the previous slide where we had powers of 1/2. Let's try an example with this. So let's say that the decay constant for strontium-90 is lambda equal to 0.0244, where time is measured in years. And we want to figure out how long it will take for the quantity P0 of strontium-90 to decay to 1/2 its original mass. So essentially what we want to find here is we want to find the time t such that P of t is equal to 1/2 its starting mass. Essentially, we want to find the half-life. So let's start with our exponential decay formula. So that's P of t equal to P0 e to the negative lambda times t. We'll use that format just so we stress that there's a negative there in the exponent. And let's fill in. We want P of t equal to 1/2 times our initial starting mass, P0. So let's fill that in. And that gives us the equation 1/2 P0 on the left is equal to P0 e to the negative lambda times t on the right. We want to solve this for t. And we notice right away that the P0s, doesn't matter how much we start with, the half-life is going to be the same no matter what. So the P0s just cancel off. We could divide both sides by P0 and cancel them. And so when we do that, we get 1/2 on the left is equal to e raised to the negative lambda times t on the right. We're trying to solve for t, so it's up there in the exponent, so we want to cancel off the e. And the way we do that is by applying the inverse function, natural log, to both sides. That's going to get our e canceled off. So we'll have the natural log and the e will cancel there on the right. And what we're left with then is just natural log 1/2 is equal to negative lambda times t on the right. And we just want to solve for t. So t is equal to natural log 1/2 divided by negative lambda. We know what negative lambda is for this particular case. Strontium-90, the decay constant lambda is 0.0244. So we could just fill that in. And so if we do the calculation there, that's perfectly fine. We could leave it like that. So in the homework, you can type in your answer like that. On an exam, you could leave your answer like that. But for the context here, let's write that as a decimal. And we would see that's approximately 28. And we want to specify the units. So we have to go back and see how is time being measured here, and we see that time is measured in years. So the units here are years. And this is the half-life. What we've done here is we found the half-life for strontium-90. All right, so we're going to stop there. We'll look at a few more examples next time on radioactive decay. We'll even look at Newton's law of cooling, which is along the same lines, and in terms of the mathematical model. And then we'll go on with a few other applications. All right, so good luck. Just a reminder, the exam 3 is this week. So if you're in Tuesday recitation, you'll have your exam today. If you're in Thursday recitation, you'll have it in a couple days. But the topics for the exam this week are on just our differentiation techniques. Learning outcomes D1, D2, D3, and D4. So just those 4 learning outcomes. Really basic derivatives, product rule, quotient rule, chain rule, and implicit differentiation. All right, so we'll stop there. Good luck if you have your exam today. Have a nice rest of your day, and then we'll see everyone on Thursday. Bye-bye.